Hello, everyone. Here we go. We are looking at some more stuff to do with gravity. So we're going to look at some weird concepts. Terminal velocity, sometimes hard to understand, but it's nothing in comparison to the other things I'm going to show you today. The idea of whether or not you're feeling acceleration when you're undergoing or giving into gravity. The look at the term weightlessness and why it's a terrible name. And we're also going to look at the so-called force of gravity. And that'll make more sense once we get through it all. So let's look at the idea of terminal velocity first. Let me just go to my videos here. Video for you. Terminal velocity. Let's go terminal velocity of a skydiver, right? Yeah.
When a skydiver jumps out of a plane at 3,000 meters, her speed goes through some big changes.
Still notice the speeds increased for quite a while, and then they're staying steady at about 55 meters per second. And then decreased to a much slower terminal velocity of about 5. So they'll show later on the idea of the forces and so on. So here we go.
Before the skydiver jumps, the floor of the plane provides a counterforce, which balances the downward force of gravity.
So think of F net, the red one and the green one would add up to 0, 0 acceleration vertically, right? So F net equals 0, acceleration equals 0. Once the red force of the bottom of the plane is gone, you're going to accelerate due to gravity.
Right? Gravity immediately pulls her towards the ground, and she starts to accelerate downwards. But air resistance is acting in the opposite direction. The faster she falls, the greater the air resistance. Eventually, the upward force of the air equals the downward force of gravity.
Once again, you've got a net force of 0, and so you've got 0 acceleration vertically. And so, yeah, you're in constant motion. You're in what's called terminal velocity. You're at the fastest you're going to get going. If you tuck your arms together, obviously you can increase your terminal velocity by decreasing your resistance, your air resistance, and then gravity can accelerate you some more. So you can control it a little bit, but really terminal velocity is just a
When forces are balanced,
thing, right?
the speed remains constant. That doesn't mean she stopped falling. It means she stopped accelerating.
Yeah, 0 acceleration does not mean you've stopped falling. Then, when you open the parachute,
to slow down, the upward force needs to be greater than the downward force. When the parachute opens, air resistance suddenly becomes much greater than gravity. The forces are no longer balanced.
So now you've got a net force up, your velocity's down, and so we know that causes you to slow down because they're in the opposite directions, as we've talked about with our direction of acceleration lesson, and so on, right? And eventually you slow down to the point where now your air resistance is going to match your gravity. You're making your air resistance get smaller and smaller until they're balanced again.
Balances gravity again, and she reaches a much...
So now those are the physics concepts of terminal velocity that we are well equipped to understand, of course. So you've got the idea of when you're accelerating down at full 9.8, you have your force down, right? And then with some air resistance, you're going to have the force of gravity balanced by a little bit of an upwards force, and so on. Let me just get this kind of match here, right? So, oh boy. And same kind of arrows, just different sizes, right? So eventually you get to the point where your upwards arrow matches the size of your down arrow. Probably close enough there, right? You get the idea, hopefully. Yeah, and so now you've got a net force of 0, right? So obviously in the first case we had just F net equals just Fg itself. Put my labels on here. assembly line process. We've got the force of air resistance. So something like that. Clone that because I'm lazy. Yeah, so in each case you've got, in this case you just have F net just equals gravity, right? There's no air resistance yet, so it's just the Fg. There's no air resistance yet because you're going slow. R for short. And then here, so there's none of these guys here. And then in this one, of course, you've got F net equals the Fg plus the force of air resistance. And this is a large number. Should maybe use red there, but let's delete that and try again. Do that for now. So this is a large number, and this one is a small number. In fact, you could say it's a large positive number and a small negative number. Positive in the downward direction in this context just feels right, I think, but depends how you want to think of it. And then same thing here. We've got, well, same idea here anyways. F net equals the Fg plus the force of air resistance. And they're the same size now. One's positive, one's negative, right? So this one's a positive number, and this one is a negative number. Or a different direction system if you choose. It could be negative and positive instead. But anyways, these add to 0, right? So in this case, we have F net equals 0. We know F net equals ma, of course. And so you can tell that means you've got 0 acceleration. And so on. So it's a lot of analysis to do with terminal velocity. I think it's pretty easy to understand overall, though, based on what we've looked at. I've done in the past a neat activity. Happened to be a really nice snowy day, and these snowflakes were coming down with nice terminal velocity. So we did this one right here is the one we measured. So you could measure that constant velocity. You get the timestamp in seconds from the slow motion. And you've got the motion here, so you could pause wherever it was. Even that one there. So get a bunch of motions, a bunch of measurements. It's kind of a neat activity. I've done in the past with classes, but certainly doesn't always work out for a nice snowy day like that on terminal velocity day. So anyways, just neat. I'm not going to make you do a lab to do that or anything, don't worry. So the next part of this lesson, your brain's going to try to tell you that I'm lying, basically. It's going to try to prevent you from understanding this. Your everyday experiences seem to contradict a lot of the stuff I'm going to show you. I'm going to actually start out just showing you some counterintuitive things to start out with here. Typically, if I ask people which rectangle is darker, people would say this one. But if I move this rectangle, I'll actually just clone this one so you can tell it's the exact same rectangle. You can tell it's the same color. There's no tricks going on here, right? The only thing that's tricking you is your brain is trying to figure out darknesses of things in comparison to what's around it. And so this one seemed lighter in comparison to what's around it. And so it's a pretty easy one to understand. In this case here, they're asking like which square is lighter or darker. People typically would say that the B square is the lighter one, right? Because they're in a shadow area, and so if it looks that bright and it's in a shadow, then it must be a brighter thing. But if I take that A square and B square, you'd be like, oh, they're actually the same brightness, so it's the same effect. Your brain just getting confused by contrast effects. Same thing with this. Which one's darker? If I were to do like a quick screenshot of this, take that piece there, and I probably should actually just take a section from the middle of it. So anyways, that's just a screenshot of it, and you'd be like, oh, they're actually the same brightness. Just, again, your brain just getting confused about contrast. Okay? Another example of your brain getting confused. There's the moon high in the sky. There's the moon in the horizon. Why is that moon so large when it's near the horizon? Or the better question is, why does it seem so large? Because the answer is that unfortunately it isn't actually larger. If you were to do the astronomy trick of measuring the number of degrees, you stick your pinky finger up and you find you can cover up the moon in this situation. And guess what? Your same pinky finger actually covers this one up, believe it or not. Try it sometime. Okay, make sure to try it sometime if you don't believe me. Um, and it turns out the number of arc seconds here, or whatever, arc minutes, is like half your pinky finger, really, but you can cover it with your pinky finger easily. So if you hear someone saying that, oh, it's magnified because it's near the horizon, that's not true, right? There isn't a magnification effect due to refraction, due to it's near the horizon, to make it look bigger. If there is any magnification effect, it's in effect all the time, right? So it's just your brain trying to make sense of the world around it in terms of what's far away and what's close up is what's messing up your brain this time. And this is an amazing picture that I found that shows this. The question is to ask you to talk about the sizes of the vans. Clearly, this one's way bigger, right? But check this out. Okay, here's a little screenshot of that sucker. And guess what? Brain's getting tricked. This is a crazy one. Couldn't believe when I saw this how effective this is. And if I put a third van back there, it's gigantic, right? All your brain is doing is interpreting this van as being farther away. And so if something looks just as big as when it's close to you, when it's far away, then it has to be gigantic, right? I'll say that again. Like if something looks just as big to you, even though it's super far away, it has to be gigantic. So like I tried to do in the past, like drawings of trees, if I drew a tree here, I'll just do, there's my whole, I better do it with the actual smartboard. My mouse drawing skills are even worse than my art skills here. So there's that little tree on the side of the road. Just undo what I just did by accident there. Z. What did I do? What I did there. Wow. All sorts of messed up right now. Oh, it's just the page rearranged on me. I get it now. Don't worry about it. So this guy here, where's my little tree? Did it go somewhere? Oh, yeah. So let's make a little tree here. Even smaller one this time, but make it a little bigger. And if I clone that thing, I don't know if it'll show up here or not. And put that tree way back there. Yeah, it does. Right? That looks like a gigantic tree. It's just your brain trying to make sense of the world around it based on what's close up and what's far away and how big the relative sizes are. Right? It's the same size, just when you put it over here, it looks like it's like bigger than the truck, right? Whereas here it was smaller than the truck, and so on. Right? Smaller than the truck, especially if it's up here. It's a tiny little one. Anyways, weird stuff. It's just the way it is. That's how your brain is trying to interpret things. Here's one I just saw recently on Facebook, right? The little monster being chased by a big monster, or is it? You look at this, that other monster is the same size, right? Anyways, so the next one here that I'm just getting you ready for the fact that your brain can get tricked, right? So your brain has been trying to make sense of gravity around you its whole life, right? And so that's why it's going to be hard to sort of feel good about things I'm going to show you next. So in the video I'm going to play next, I'm going to have my smart cart, and it's going to be accelerating to the right, and then it's going to be slowing down. So it's going to accelerate to the right, then to the left, and I'll do it again later in the video. Okay, so let's do that first. Let's just get that guy up, and I'll just mute myself here because I don't need to talk over the video. So basically I'm saying I'm going to make it accelerate to the right. So I'll just play that again. There we go. You see real time here, accelerating to the right and then to the left to slow down. So speeding up and slowing down right after one another, right? So you got that. And then the trick is I'm going to take this cart, I'm going to move it vertical. Okay? I'm going to line it up so it's straight up and down. And it's not going to be accelerating, it's just going to be sitting there in front of the camera. What's the accelerometer going to say? We know the accelerometer is active here and making measurements of acceleration to the left and the right. So now we're talking about acceleration up and down, right? So let's see what happens. There we go. All right, so it's stationary clearly. And look at that right there. I'm going to zoom in a little bit here in a second anyways too, but that acceleration right there, notice, is just under 10. Okay, it's about 9.8, one might say, 9.83 even. Um, Obviously, you recognize that's the acceleration due to gravity. So that cart sitting there in this position, the sensor thinks it's accelerating up, right? Here in this situation, it felt acceleration to the left and the right, or right and then left, or whatever. In this situation, it's feeling acceleration up the whole time. Why? That's kind of weird, right? Well, let's figure it out. Okay, so the result, of course, is this, or it has this 9.8 up the whole time. Well, it turns out that feeling that normal force, with my hand in this case, holding the car up, or your chair holding you up, if you're sitting down in a chair, right, that normal force up, you feel that force on you. And so if you feel a force on you, then it's going to feel like acceleration. If you F equals ma, right? So this shows that the normal force up on the sensor, right, is the same as an applied force that makes it feel accelerating to the left or the right. So the normal force is up, and so it feels like acceleration up. So this is hard to swallow. It's hard to accept. But Einstein realized this fact of the world around us, and it led him to his theory of general relativity. Okay, so general relativity is all about the fact that you can be experiencing gravity or you can be experiencing acceleration due to a force on you, right? So and they're equivalent. You can't actually tell. There's no experiments that can determine whether or not you're in a closed box with no windows and you're on Earth, or whether you're in a closed box with no windows and there's a rocket underneath you accelerating you up at 9.8 meters per second squared, right? So that this little video here, equivalence principle, shows the idea that if you launch a rock or an object sideways on Earth, of course it's just going to go with horizontal projected motion. If you're in a rocket blasting up at 9.8 meters per second squared, it'd be the same effect. And that's what I mean by you can't actually. There's no experiments you can do within a sealed system here to tell whether or not you're actually experiencing gravity or whether you're experiencing acceleration. And that's Einstein went with that and developed the equations to general relativity, which are pretty crazy. It's a pretty crazy accomplishment that he did back in I don't know, early 1900s, right? So experiencing a normal force to balance gravity feels the same as acceleration, right? So you're feeling a force up and on your feet, therefore you feel like you're accelerating. Of course, relative to the Earth reference frame that you're very aware of and familiar with, you are not accelerating, right? And so your brain tricks you into thinking you don't feel like you're accelerating, even though you do. Okay, so think of the sensation of feeling the back of a seat push you forward if you're in a car that's accelerating a lot. I went for a ride recently in a friend's Tesla, and oof, you felt the push of the seat forward. The only time I felt like that in the past was my dad's 1998, I think it was, Grand Cherokee with like a 5.8 liter Hemi in it, and you could always feel the push forward. Right, that's feeling acceleration. Well, right now you're feeling a force up on you, unless you happen to be falling. Hopefully, you're not falling. Right? If you feel a force up on you, you actually feel like you're accelerating up, right? So I'll get to that here. Oops, I don't want to delete. So it's hard to believe because your human brain tries to make sense of the world around you, just like in the optical illusion things or whatever you want to call these things I looked at earlier. And ever since birth, you felt that normal force, and that normal force you're feeling means that you're not accelerating relative to Earth. So your brain just says, okay, well, that's what not accelerating feels like, basically. It just kind of leaves out the relative to Earth part, right? It doesn't make that distinction. Okay, so your brain's thoroughly convinced that the normal feeling of having a force up on you indicates you're not accelerating. And, more importantly, you end up you end up feeling like you don't think you feel like you're accelerating. If that makes sense. Okay, so you're not accelerating relative to Earth, of course, but you are actually feeling an acceleration and a force upwards. Okay, so your brain is messed up on this one, just naturally based on your upbringing on Earth. So which leads us to, I'd be curious actually, in a future civilization, someone born and raised in outer space, there's health issues with this, of course, but I mean, first time you'd experience gravity, it would probably be much different than what we think of it as, right? They'd be very aware of that force upwards on them. So the question is, as a result of this, do you feel like you're accelerating while you're falling? Do you feel like you're accelerating while you're falling? So the question is, do you feel a force on you when you're just falling? You jump off of a cliff to go cliff diving into the water or whatever. The answer is, well, no, you don't feel a contact force on you. You don't feel the gravity force at all. No force is felt. You don't feel something pushing down your head. You don't feel something pulling on your feet, right? You just fall. You just accelerate towards Earth without feeling a force. There's a clue there as to some reality I'm going to share with you later. So you don't feel like you're accelerating. You just know you're accelerating because you can see you're going towards the Earth faster and faster, but you don't actually feel like you are. Okay, like again, your brain has tricked you and so on, right? You see the ground coming faster and faster and the wind passing you faster and faster, and so you clearly are accelerating relative to the Earth, and so that's your interpretation, right? This video here shows what happens when I drop the cart. Okay, so here I go again. So dropping the cart, and then while it was falling, what was the acceleration reading? So you'll see that while it was falling, right there, it's at an acceleration of 0 while falling. That little time interval there of about a half a second or so. Okay, that is what we're talking about. But you actually don't feel like you're accelerating when you're falling, even though it's your brain makes you think you do, right? But that's the number right there. Okay. So if you ever have a chance, to do this and think about this, you jump off a cliff into water safely and whatnot. While you're falling, you have to shout out, I can't feel a force on me, so I don't feel like I'm accelerating. See how many times you can say it on your way down. And I've had students send me videos or tell me, some people send a video and that other times they're like, oh, I did it. And it's true. I really couldn't feel like I was accelerating, but it's hard because, you're rushing towards the water and you don't want to break your neck, So something to think about next time it's summertime, jumping off something into the water. So what do I have here? Having balance forces vertically and 0 acceleration relative to Earth, right? So we have these balance forces and so on, right? We've got an upwards force and a downwards force, vice versa here, right? We feel this force up, and so we feel like we are accelerating. In comparison to if you have other situations where there's no force, right? And it feels like no acceleration. So no force and no acceleration. If you're looking at horizontally, obviously there's no force, there's no acceleration felt. In so-called weightlessness, which we're going to talk about next, right? You don't feel a force, and so you feel like you're weightless. Really, you don't feel a normal force on you. In the vast emptiness of outer space, far away from any planets or masses or anything. In other words, there's like no gravity effect on you whatsoever. You're not going to feel a force on you there unless something's pushing on you. You don't even have to be actually far from masses. I'll show you soon. Okay, but anyways, keep going here. Weightlessness. We said we were going to talk about this, right? So on the International Space Station, the acceleration due to gravity must be 0, right? Because you're weightless. Well, it turns out it's actually 9.07. It's like 90% or something like that of the original value. It's not much of a reduction, really. You're still very much attached to Earth gravitationally, even way out in the International Space Station, which is like 400 or 500 kilometers or something above the surface of the Earth. Not actually really that far in comparison to the size of Earth, really, but you're a good ways up there. You calculated recently, yesterday, I guess it was, last lesson, the weight would be 588, and then the weight up at 400 kilometers above would be only 521. Well, clearly that's not weightless, right? 87%, around 90, like I said, right? 87% of your actual weight still. So you're clearly not weightless. I'm going to show some videos here that maybe help to understand better why you feel weightless, why you think you feel weightless. And so let's run through those. I'll see if I survive copyright things for this. Anyways, so explanation of weightlessness. Here we go. Weightlessness in orbit. There we go.
Are travelling so fast that they're in perpetual free fall as they orbit around the Earth. But what is an orbit? Down here on Earth, even a high-velocity bullet will hit the ground at about the same time as the ejected cartridge.
We saw that later, or earlier in the course.
Gravity wins. But imagine that you could have a super high-velocity bullet, and that you could strip away the Earth's atmosphere to eliminate drag. Then the falling bullet would follow the curve of the Earth and never hit the surface. If you weren't careful, you'd shoot yourself in the back. Sealed against the vacuum of space, the crew are inside a huge bullet, the orbiter, traveling at 10 times rifle speed. They and Discovery are falling around the Earth at exactly the same rate. So the astronauts float around in...
So the astronauts and the space shuttle they're in, or whatever craft they're in, are both just traveling in that projectile motion. They're both basically free-falling towards the Earth.
Inside the cabin apparently weightless, even though they haven't escaped from the Earth's gravity.
So apparently weightless because, like I said, they still have 87% of their actual force of gravity, which is their so-called weight, right? And I want to show, like, picture them, you know, traveling in a path. There's the video I'm going to show you in a second does this as well. But picture the Earth, right? And you are, you know, here you just fall to the Earth. Well, if when you fell to the Earth, you ended up moving over this far, then you'd still be orbiting, right? And then you fall here, you move to there, and so on. You just basically keep falling, but you keep traveling sideways. Well, that's what orbit is, right? So I think I can probably skip this video because that's essentially the gist of the story on that one. I want to jump ahead. Actually, I'm deciding I want to do this here. I'm going to show you projectile motion motor graphs here. Recent reel I saw on the Facebook. Let's go to my videos here. See if I spelled that right or not. Yeah, it looks like it did. So right here. So right now it's in slow motion a little bit. Look at that. Right there, right there, right there, right there, right there, right there. They're just traveling in projectile motion together. So he's not sitting on the bike anymore. Is he weightless? Clearly not. He's accelerating towards the ground. You know, it has the force of gravity on the person, you know, like it's that, but that's the same effect as so-called weightlessness in outer space. It's just that you end up hitting the Earth. So that, when I saw that video, I was like, okay, I have to get a copy of that and show that, because that is perfect for showing what I'm talking about here. So this description, why are astronauts weightless? So why are, see if I can get away with just why are here. Are astronauts weightless? Perfect.
Have you wondered what it would be like to be an astronaut floating around in the space station?
But why are the astronauts floating? I'm here at the Powerhouse Museum in Sydney to find out if anyone knows the answer. Why are they floating?
No gravity.
No gravity.
Zero gravity.
There's no gravity.
Gravity.
There's stuff that holds.
By the way, the other word is, of course, zero gravity, right? Or, you know, weightlessness or zero gravity or microgravity. 87% of gravity is not really that micro, though.
To the planet when we spin doesn't.
This guy's saying the stuff that holds you.
Gravity holds you down.
That holds us to the planet when we spin doesn't happen up there.
Gravity holds you down, so in space there's nothing there, so you just float.
There's no gravity in space.
There's no gravity, or there's very little.
But is there really no gravity in space? After all, the moon orbits the Earth due to gravitational attraction. So where would the space station fit in this picture?
Can you make me a roughly to scale model of the Earth and the Moon? And then we're going to position the space station in there. So about like that?
Closer. Now, there.
You ready to see the real distance? What do you reckon?
Oh, okay.
Actually, about here, maybe a little further. I think we were wrong. Now, if the moon is here and the Earth is there, whereabouts would you put the space station?
Somewhere around here.
Really?
About halfway?
Yeah.
Right about here? So that's maybe like a quarter of the distance to the moon. Let me show you the real distance. Are you ready for the real distance? The space station is right about there.
Oh, okay,
Right
that's
there.
close.
So the point is, of course, gravity's holding the moon. Clearly, there's still gravity in that point, that spot, so close to Earth, right? And so I think end up showing. No, not really. So I'll leave that one. But the idea of what I wrote on previous slide here of the falling down towards the Earth, but you end up going sideways, might show this one after all. Why do astronauts feel weightless? Let's feel weightless. So this guy here shows, that if you were to climb a big ladder, you still got like 87, 89% of your weight, right? And then, if you jump off the ladder, you just accelerate towards the Earth, obviously. But if you have a huge sideways velocity, then you can end up going to the side of the Earth and going around and around. And that's what orbit is. Okay, so same idea. That's what I showed. Yeah, basically zero gravity, weightless, microgravity. They're all terrible names for this, really. Better name would really be what's missing. Remember this? The motorcycle, the guy was, not sitting on the seat anymore. There's normally a normal force that holds the person up. That's why they call it that, right? Against, from the seat on the guy's butt. And, instead there isn't one, right? So really the better name would be normal forcelessness. Better physics wise, at least, right? Maybe it doesn't roll off the tongue, tip of the tongue, and people might not understand why you're calling it that. But maybe if we always just called it that, maybe we train people better to understand the physics of the world around them, maybe it'd be a better world. But yeah, there's no normal force needed to hold you up in that scenario. So you're really in normal forcelessness is my vote for the name. So realize that there is, of course, a force of gravity on you. For weightlessness, realize that the space capsule also has the appropriate force of gravity on it. And so they're just accelerating at the same rate due to gravity as all masses do. And so they're just falling together relative to Earth, right? They're just falling together. So when you have so-called weightlessness, really you're just freely falling under the force of gravity. And so you don't actually feel like you're accelerating like we talked about, which is really clear when you see the pictures of people floating around in so-called weightlessness, right? So if you're to picture in this drawing, wherever it was here, if you have like a camper trailer and it's launched sideways and it's falling towards the, someone you'd be in orbit inside of a camper trailer. Well, no different than if the camper trailer is just plummeting towards the ground and you're plummeting towards the ground with it, right? So picture I have a camper trailer drop off a cliff, and you and the camper trailer are dropped, beside each other, right? Well, what if you're inside of it and falling? Well, you're both accelerating at the same rate, right? So you'd just be falling inside of it, floating around, enjoying weightlessness, plummeting to, bottom. But, it's not the fall that kills you though, right? It's the sudden stop at the end. That's a unit from the grade 12 physics course, actually. Momentum and impulse. Anyways, so this is the picture we want to have, right? Whether it's a motocross bike that's going in a parabolic arch and you're going along with it, or whether it's a space shuttle or whatever you call it, space station going in orbit and you're going along with it. You're just so-called weightless inside of it. You can simulate this with airplanes. You can drive in a parabola shape, and the parabola shape is, of course, the shape the plane would go in if the engines were all off. No wings, no thrust, no lift. And so you and the plane just sort of travel in that path. It's called the vomit comet. So the zero gravity training here. Zero gravity training. Which one do I want here? Zero gravity. Underscore maybe. There we go. I know which one I'm getting here. So this is just a training video from a training exercise where they're inside of the plane. And so the plane and them are all just traveling a natural parabolic arch. It's like they all just got shot out of a cannon, basically. The plane and them are just floating along in space. And so it's just training astronauts what it's going to be like to be in the space station floating around with so-called weightlessness. I always say so-called weightlessness because you're not actually weightless, right? This one's hilarious. Astro Dog. Oh my gosh. Oh, favorite. One of my favorite videos. Astro Dog. So these two goofs here, flying in their little Cessna or something like that, and they travel towards the ground with acceleration due to gravity, basically. And there's a dog in the back. They're all strapped in, right? The dog apparently has done this before because didn't really seem to care. He's like trying to lick the guy's ear, right? Hilarious. Love it. So Astro Dog, and then there's the motocross video. Okay, so hopefully that is making sense. I'll just I think we get it. I think I'll leave that video for you if you can watch it as well if you want. We already did the Astro Dog. On a roller coaster at Canada's Wonderland, the Behemoth does this really, really well. So Six Flags, I'll type in. I haven't done a video like this myself yet because I don't want to get kicked out of the park. But these guys took the chance here, and they're going along the roller coaster. And the guy lets go of the tennis ball when everybody else is like, woo, we feel like we're weightless, basically, right? Or so-called weightless. Watch this. And so he lets go of the tennis ball, and the tennis ball just like floats in front of him for the half second or so because they're both just traveling in a parabolic arch. There it is. I probably would have like tied a string to it just to, make sure I don't lose it and whatever and hit someone with it. But, that is pretty cool that they managed to do that. So there's no normal force needed in that portion of the video, right? Because they're both traveling in a regular parabolic arch, right? So if you're holding on to the tennis ball stopped somewhere, whatever, you have to hold a normal force up on it to balance gravity. But when you're traveling, just traveling in a parabolic arch, you and your surroundings, or you and the ball, you don't need to have a force on you to go against gravity. All right. So Astro Dog, there's a bunch of videos I've shown in the past, but we don't need to see those. All right. Okay, so one more thing I want to share with you. Before I do that, well, I guess two more things, but whatever. So I'm going to share something about gravity as well, but first a little bit more about forces themselves. In the past, I've mentioned that we have these like contact and non-contact forces. So contact forces being like pushes and pulls and friction, and muscle forces like a push, and elastic forces like a pull from an elastic or a hit if it hits you, I suppose, and so on. Mechanical forces, like there's all sorts of names for so-called contact forces, right? And then I did mention the idea of non-contact forces, right? The strong nuclear force, the electromagnetic force, the weak or electroweak, they call it. Actually, that's when you join the two, but and the gravitational force, going from strongest to weakest, right? What I didn't share back then is that really contact forces aren't even actually contact forces. So contact forces, where did I put it? It's still in downloads. There we go. Move it over to my files yet. So the question.
Touch anything?
So it says,
do you know that at the atomic level we cannot touch anything? Each atom has a nucleus in its center, and around this nucleus there is an invisible field in which electrons move.
Electromagnetic
When
field.
two objects' atoms come close to each other, these fields push each other, which gives us the sensation of touch. But in reality, it's not touch, but a repellent force between the two atoms. Do you know?
So just give me a sec here. All right. Sorry about that. Back on track here. Yeah, so there's contact forces that you think of as pushes and pulls are actually really just repulsions from the electromagnetic force, really, at a subatomic or at an atomic level, I should say, really. The non-contact forces. So how do they work? Since everything's really non-contact forces, action at a distance, as some people say. So if you're looking at all the different forces, these so-called non-contact forces, or actual non-contact forces, the strong nuclear force, all these ones are mediated or carried by exchange particles. Okay, so the idea of an exchange particle we saw when I showed you the video of a medicine ball being tossed back and forth between my two students. And so the medicine ball like pushes, the one person pushes on the medicine ball, the medicine ball pushes on them, and then they catch it, and the medicine ball, repulsion is really easy to picture. A boomerang could be something that could cause a attraction force, right? You whip the boomerang that way, you get a force together. When the other person catches it, gets a force towards the center. You get these like action at a distance particles, all right? The particles that are, oh, no, I didn't need to move that. The exchange particles for these things. I might have talked about this before with you. They're called the gluons because it helps glue the nucleus together. That's how imaginative physicists are. The electromagnetic force is actually photons, particles of light, basically, that are the particle that carries the electromagnetic force. And the weak force is carried by forces called bosons, the W0 bosons, and so on, called vector bosons. Vector because they're cause forces, right? So they're carried by exchange particles, and this is very well experimentally confirmed. It started out with the electromagnetic force. They analyzed it, and they came up with quantum electrodynamics, which is basically a bunch of math equations that perfectly describe everything to do with electromagnetism, and it's all based on exchange particles. And then they copied that idea and worked out an amazing formula for the strong nuclear force called quantum chromodynamics. And it's just really cool stuff. It works amazing. It's like amazing experimental confirmations and so on. Okay, so this idea of exchange particles for how action at a distance works, very well understood. Look at gravity though, and gravity, they say, okay, well, let's call the exchange particle for it the graviton, not to be mistaken with the ride at the fair called the gravitron. So the graviton is the possible exchange particle for the gravitational force. It has not been experimentally confirmed. And in fact, there have been experiments where they think it should have confirmed them, but it did not. Some say that the graviton can't be detected. Philosophers would look at that and say, well, if something that can't be detected, it's because it doesn't exist. So maybe this next thing that's the weirdest of all won't be that crazy after all. But the title of the video kind of gives it away, is why is gravity not a force? All right, so let's look at that one. Not, and I'm looking in the wrong folder right now. Copy videos. So, there we go. There we go. I'll have to skip a little bit through this, I guess, but side.
This video was sponsored by Caseta.
Let's jump ahead a bit.
Of his life was.
There we go.
Albert Einstein said the happiest thought of his life was imagining a man falling off the roof of a house. What made Einstein so happy about this wasn't Schadenfreude. It was the realization that this man, while he was falling, wouldn't feel his own weight.
Schadenfreude is like a German term for like taking pleasure out of other people's misery or something like that, I think, right? But so it wasn't that. It was actually...
He would be weightless. And anything he dropped on his way down,
so-called
it
weightlessness,
would remain stationary relative to him, or moving in uniform motion. The whole situation would be just like if you were in deep space, not near any large masses, with your spaceship at rest or coasting along at constant velocity. Here, you would feel no weight. Objects would remain stationary relative to you, or if you give them a push, They would move in a straight line at
That would actually be weightless in that scenario.
constant velocity. And you would be the very definition of an inertial observer. You're not accelerating, not in a gravitational field. All the laws of physics apply in your reference frame, meaning there is no experiment you could do to distinguish your inertial reference frame from any other. Now, here comes the big leap. Einstein looks at these two scenarios and says they are equivalent, not just similar. Physically, they are exactly the same thing.
So in this scenario, the person is near Earth, accelerating due to gravity. This person is nowhere near Earth, out in the middle of space, no gravity at all. They are equivalent. There's no experiment you can do to determine which one's which. Okay? If you had inside of a closed box, no windows kind of thing.
Which means man falling from roof is not in a gravitational field. There are no gravitational fields. And he is not accelerating. He is...
So we're already good with the not accelerating thing, I feel. But he's going a step further to say that there is no gravitational field. There's basically gravity is not a force. Okay?
An inertial observer, just like Rocket Man. Whoa, whoa, whoa. I mean, okay, I can see how both of these observers feel weightless. But man falling from roof is clearly in a gravitational field. I mean, he's right next to the Earth. And he's obviously accelerating. His speed is increasing by 9.8 meters per second every second, a fact that will become painfully apparent when he crashes into the ground. I know that these two situations look very different, but Einstein's equivalence principle tells us the one thing to focus on, the experience of the observer. If they feel weightless, then they are in an inertial frame of reference, every bit as good as Rocket Man's out drifting through deep space. Imagine if Rocket Man, coasting along at constant velocity and not paying attention,
this is really good, okay, to help see why this is.
Comes upon a planet a long way off in the distance. An external observer might notice that the path of the rocket bends ever so slightly towards the planet. But inside, Rocket Man would remain oblivious. He feels no force, experiences no acceleration. As the rocket gets closer to the planet, it goes faster and faster. But Rocket Man still feels weightless.
Just like we're used to, right? The rocket and him are just both accelerating towards the planet, relative to the planet. That's not incorrect to say at all.
For him, nothing has changed. So where on this journey would you say the frame of reference changes from inertial to non-inertial? An onboard accelerometer would never even register a blip. He has continued on his inertial path through space-time. So the logical conclusion is his frame of reference is inertial up until the instant he crashes into the planet. Okay, so how do you explain the curved path of his rocket without gravitational forces or gravitational fields? The answer is curved space-time.
So the key component of Einstein's theory of general relativity was that gravity is in fact really just an experience we have due to the curvature of space-time. Universe, the fabric of the universe, space-time.
First, focus on Rocket Man's observation that the whole time he felt like he was moving with constant velocity in a straight line. He was moving in a straight line through space-time. But space-time around massive objects like planets is curved. So that's why his path appeared curved to a distant observer. Now, this isn't as unusual as it seems. Airplanes, for example, always try to fly the shortest route between cities. Essentially, they just go in a straight line. But since the Earth's surface is curved, the shortest path doesn't look like a straight line. These shortest paths over curved surfaces are called geodesics, and we use that same word, geodesics, for the straight line paths followed by inertial observers through curved spacetime. Here's another analogy. Imagine you and a friend are standing 1,000 kilometers apart on the equator. Now you both set off due north. Over time, you will come closer together, ultimately bumping into each other at the North Pole. It's as though there was a force pushing you together, but you didn't feel a force, and your friend didn't feel a force. Gravity is just like that force. It doesn't actually exist. The real reason for you coming together was that you were both on straight paths, geodesics, on a curved surface. Astronauts on the space station are weightless. that means they too are
So-called weightless.
inertial observers traveling on a geodesic. But the Earth curves space-time around it, which is why their straight-line path appears as a helix. It only looks like a circular orbit if you forget the time dimension. Don't forget, we are all moving through space and time. Space-time. This is the standard bent sheet analogy for curved spacetime. But I think this demo is misleading. It allows you to fool yourself into thinking you understand general relativity when the intuition you're actually drawing on is just that objects like to fall towards the middle of a well due to the gravitational force. But in general relativity, there is no gravitational force. What you should be thinking about is objects traveling on a straight line path through spacetime. It just so happens that space-time is curved around massive objects. So that straight line path doesn't look like a straight line. Matter tells space-time how to curve, and space-time tells matter how to move.
Mic drop.
Now let's go back to deep space. What happens if you turn on the rocket thrusters and accelerate at 9.8 meters per second squared? Well, someone outside would see all objects remain stationary, while the floor of the rocket accelerates into them.
Now you'd feel like you have a force on you, right? You'd feel, like if you're accelerating at 9.8, you'd feel like you're undergoing regular gravity. So I think that's enough for what I want to do here. I just wanted to share with you that gravity is not actually a real force. It's not mediated by exchange particles that by all experimental results. This is a bit controversial. Not everybody would agree with what I'm saying, but this is what the evidence is leading towards, basically. And so we have like these fundamental forces, and then you have like the effect of gravitational force because of what we're used to living on, a giant mass. But there's a basically in trying to find the grand unified theory of all the forces, like electromagnetic and weak, there's electroweak, and then the grand unified theory would try to include strong nuclear force as well. I don't think it'll ever include gravity, because I don't think they're going to find a graviton. I don't think that it's a real force. So there you go. But yeah, feel free to watch the rest. I'm going to be careful when I'm posting this and see if I get away with copyrights, but if not, it won't look much different to you. It'll just be playing through the media center instead of through YouTube. So if you're going to, I guess I can't tell you this during the video, but if you're going to look for this video on YouTube, it might not be there. Yeah, so there's that. And yeah, thanks for watching. And I don't have an assignment for you for this one. So I hope you enjoyed, and hope your mind is sufficiently exploded. And I hope you can watch it again and think about it further. You probably have to watch it 17 times to end up have it feel like it makes sense, because it takes a while for your brain to just kind of get used to the weird ideas. So, all right, thanks for watching.